Hello, I'm Mireille Soergel. I'll tell you about systolic complexes and group presentations. Systolicity is a combinatorial form of non-positive curvature, and I'll build such complexes using Cayley graphs. To be more precise, a simplicial complex X is systolic if it is connected, simply connected, and the link of any vertex is flag and 6 large. A flag complex is a complex in which every set of pairwise adjacent vertices spans a simplex. So a flag complex is uniquely determined by its one skeleton. And if I give you a simplicial graph, so a graph without loops or double edges, I can always build the associated flag complex by filling in every possible simplex. A complex is 6 large if every embedded cycle gamma of length 4 or 5 has a diagonal. An embedded cycle is the image of an injective simplicial map of the triangulation of the circle into a complex. Its length is its number of edges, and it has a diagonal if there's an edge between two non-consecutive vertices. The examples I will be considering of simplicial complexes X will always be complexes where the X is always a flag complex. That means that X will be uniquely determined by its underlying graph. So that means that first, the link of any vertex will be the subcomplex spanned by the vertices adjacent to V. Moreover, if X is flag, so is any subcomplex of X, so the link will always be flag. So we will only need to see if X is connected, simply connected, and if the link of any vertex is 6 large. First, let me give you examples of systolic complexes. This image here is the triangulation of the Euclidean plane. First, note that this is a flag complex because I have here 3 vertices that are pairwise adjacent, and they span a simplex. And for every such 3 vertices, they will span the corresponding simplex, so this is a flag complex. Second, it is the Euclidean plane, so it is connected and simply connected. What is the link of a vertex? Consider the blue vertex here. As we said, since this is a flag complex, the link is spanned by the vertices adjacent to this blue vertex. So it is spanned by those red vertices. So the link of the blue vertex is this red subcomplex. This is a cycle of length 6. There are no embedded cycles of length 4 or 5, so the link of any vertex is 6 large. Hence, the triangulation of the Euclidean plane is systolic. Let's look at this second example. The icosahedron is a triangulation of the sphere. This is also a flag complex. It is connected and simply connected. And the link of the blue vertex here is spanned by the vertices adjacent to it, which are those red vertices. So again, the link is this red subcomplex. This is flag, but the problem is that this is a cycle of length 5. And it doesn't have any diagonals. So this is not 6 large. So the icosahedron is not a systolic complex. We say that a group is systolic if it acts geometrically on a systolic complex. Geometrically means properly discontinuously and co-compactly. Let me give you some properties of systolic complexes and of systolic groups. Systolic complexes are contractible, so they work as classifying spaces for groups. I told you that systolicity is a form of non-positive curvature, while two-dimensional systolic complexes are cut zero. Systolic groups are biautomatic. Biautomaticity implies a solvable word problem, a solvable conjugacy problem, and a quadratic Dern function. Finitely presented subgroups of systolic groups are systolic. And the centralizer of an infinite order element is commensurable with the direct product of a free group with Z or with Z. Note that this property implies that that cube is not systolic, but any finitely presented subgroup of a systolic group is systolic, so any group that contains that cube cannot be systolic. Let me now get to group presentations. A group always acts on its Cayley graph. My goal is to give you some conditions on group presentations that imply that flag complexes of Cayley graphs are systolic. Consider a group G, a subset S in G, which is a generating set. Then gamma, the Cayley graph of G with respect to S, is a graph whose vertices correspond to group elements. I note them VG. And there's an edge E from VG to VH. If I can find a generator S such that H equals GS. And I always draw the following picture. This is a vertex corresponding to the element G. This one corresponds to H. And this is the edge labeled by S. To define a flag complex, we need to start with a simplicial graph. A graph without loops or double edges. A loop corresponds to an edge from a vertex to itself. So it corresponds to a generator S being the identity. A double edge corresponds to two generators being the inverses of each other. So, to have a simplicial Cayley graph, we need to require that S intersected S inverse is the empty set. Once we have this condition, we can define the flag complex of the Cayley graph. This flag complex is always connected, since the underlying Cayley graph is connected. Let us find conditions on the generating set that imply that the flag complex is simply connected. A simplicial complex is simply connected if its two-skeleton is simply connected. So that also goes for the flag complex. To build the two-skeleton of the flag complex, I need to glue in triangles in the Cayley graph. But a triangle is a closed path of length 3. So it corresponds to a relation among the generators. This relation can basically have two forms. Either it is of the form A times B times C inverse equals the identity, or it is of the form A times B times C equals the identity. So consider the set R of all possible relations of length 3 among the generators. We can make the following statement. The flag complex is simply connected if and only if the group G admits the presentation with generators S and relations R. To understand when the flag complex is systolic, we now need to understand when the link of a vertex is 6 large. Let us consider the following more restrictive setting. We have a group G, a subset S, which is a generating set. The first condition is that S intersected S inverse is the empty set. The second condition is if we have a triple ABC of generators, and if the product ABC is also an S, then the products AB and BC should be an S. The third condition is that the set R of all possible relations of length 3 among the generators should have the following form. So those relations should all be of the form ABC inverse equals the identity. In particular, this means that there are no 3 generators ABC such that their product is the identity in G. We call such a presentation a restricted triangular presentation. Because of the first condition, the flag complex is well defined, and because of the third condition, the flag complex is simply connected. Moreover, since we are in a flag complex, the link of any vertex is flag. So this flag complex will be systolic if and only if the link of any vertex is 6 large. In this setting, we can make the following statement. The flag complex is systolic if and only if the generating set S satisfies the following 5 conditions. You can only see 3 of the conditions here because the screen is too small, but they are all of the same model. Let's go through them. The first one is, if there exists UW, A, B, C, D, and S, where U is different from W, A is different from D, UA equals WB, and this product is an S, and UD equals WC, and this product is also in S, then there should exist a K in S such that UD equals UAK or W equals UK. This condition corresponds to this setting in the Cayley graph. Every element in S corresponds to a vertex in the link of the identity. So the elements U, W, UA, and UD are vertices in the link of the identity. Moreover, since A is also in S, I have an edge from U to UA. In the same way, I have an edge from U to UD. Since UA equals WB and B is also in S, I have an edge from W to UA, and in the same way, I have an edge from W to UD. Moreover, U is different from W, UA is different from UD, and A and B are different from the identity, so UA is different from U and W, but it's also different from UD. Same goes for UD. It's different from W and U, and it's also different from UA. So this is indeed an embedded cycle in the link of the identity. The second part of the statement is that there exists a K such that UD equals UAK or W equals UK. But such a K corresponds to an edge either from U to W or from UA to UD. So it is a diagonal in such an embedded 4 cycle. So what this means is that if there's such a cycle of length 4 in the link of the identity, then it should have a diagonal. The second condition says, if there exists Vx, A, B, C, D in S, V different from X, A different from B, and BV equals CX in S, and AV equals DX in S, then there should exist a K in S such that V equals KX or AV equals KBV. This statement corresponds to this cycle of length 4 here. If V and X are elements in S, then the vertices corresponding to V and X are in the link of the identity, but the vertices corresponding to the inverses, so to V inverse and X inverse, are also in the link of the identity. And in the same way, all those vertices correspond to different elements in the group. So this is an embedded cycle of length 4. So this statement says that if such a cycle of length 4 exists, then it should have a diagonal. Let me show you the 3 next conditions and the cycles they correspond to. The third condition is if there exist UVXVC in S, V different from X, UV is an element in S, as well as UX, and WB equals XC is in S. Then there exists K in S, such that X equals VK or K equals UVB. In the same way as the 2 previous conditions, this corresponds to a cycle of length 4, which should have a diagonal. The fourth condition is if there exists VWXAD in S, V is different from X, VW is in S, XW is in S, and DX equals AV, and this is an element in S. Then there should exist a K in S, such that V equals KX or K equals AVW. This condition corresponds to this cycle here. The fifth condition is if there exist U, V, W, and X in S, U is different from W, V is different from X, and UV is in S, UX is in S, WV is in S, as well as WX, then there exists K in S, such that X equals VK or U equals KW. This corresponds to the following cycle here. Let me make a few remarks about the statement of this theorem. First, all those 5 conditions are necessary. It's quite easy to build a presentation of a group that satisfies 4, but not all 5 of those conditions. Secondly, what the theorem says is that to see if the link of a vertex in the flat complex of the Cayley graph is 6 large, I don't need to check every cycle of length 4 and every cycle of length 5. I only need to check if those 5 different types of cycles of length 4 have diagonals. Let me give you an application of this theorem. Our theorem only applies to restricted triangular presentations. So we need to find groups that admit such a presentation. One class of groups to do so are Gaussian groups. Here is one example of Gaussian groups where the induced restricted triangular presentation satisfies the condition of our theorem. Pick 2 positive integers n and m. Then we define the group G and M to be generated by x1 to xn and satisfying the following relations. The product from x1 to xn of length m should be the product of x2 to x1 of length m, should be the same as the product of xn, x1 to xn minus 1 of length m. This product is defined in the following way. The product x1 to xn of length m is a product of x1, x2 until xn. Then I start over with x1 and keep going until I have m letters. I will later use this notation where this special product in the group is called delta nm. This presentation is not a restricted triangular presentation, so we need to find the right set of generators. Well, the set we should consider is a set S and M of all products xi to xi plus n minus 1 of length k, where I is greater or equal than 1 and less or equal than n, and k is less or equal than m and greater or equal than 1. You should understand those indices modulo n. So this set contains the original generators x1 to xn and all those ordered products of lengths less than m. It also contains delta. If we consider S and M as a generating set or a group, the presentation of G will be a restricted triangular presentation. Moreover, this generating set S and M satisfies the condition of our theorem. So the flat complex of the Cayley graph with respect to this generating set is systolic. We can also do this for a slightly larger class of examples. We can pick a positive integer p and construct p such groups G and M. We then consider the group G, which is the free group of all those G and M's, but I then identify the deltas from the different groups. If I consider the generating set S, which is the union of the generating sets from the G and M's, the presentation of G using S will be a restricted triangular presentation. Moreover, S will satisfy the conditions of our theorem, so the flat complex of G with respect to S is systolic. Note that G acts geometrically on this flat complex. Hence, since this flat complex is systolic, so is G. Let me finish by giving you some examples of such groups. The group G and N corresponds to the fundamental group of the complement of n lines through the origin and the complex plane. Torus knot groups, which have the presentation with generators x and y in relation x to the p equals y to the q, or some positive integers p and q, is a group of this form by using this equality. And lastly, dihedral Artin groups have the standard presentation G to n. You can note that the group G to n is isomorphic to the group Gn2. So we have two different flat complexes of Cayley graphs that are systolic for dihedral Artin groups. If you have any questions, please write on Discord or come to my office hours. Thank you for watching.